Hi, what I have here on the workbench today is a UNI-T UDP6953B. It is a professional-grade programmable DC power supply, and it can output up to 150 volts and 10 amps with a maximum output power of up to 600 watts. Thanks UNI-T for sending me this unit to review. UNI-T also sent me another power supply. I'm not going to review which model that one is just yet. If all goes as planned, I will be reviewing that unit in the upcoming video in the next couple of weeks. So be sure to subscribe to the channel and enable the notification so that you won't miss that review. This is a switching power supply, and because of that, it weighs only around 4 kilograms or 9 pounds. So you can see that it's relatively light for a 600 watts power supply. In UNI-T's UDP6900 series lineup, they have quite a few different models, which you can see on the screen here. The maximum output voltage is either 60 volts or 150 volts, and the maximum output power ranges from 100 watts all the way up to 600 watts. And price-wise, these power supplies are not cheap, as they are professional-grade ones. At the time of making this video, the retail price ranges from just above $500 for the UDP6923B, which is the 60 volts and 5 amps one, to all the way up to above $1,500 for the UDP6953B, which is the one we have here. Yes, the price might be many times over the budget of what an electronics hobbyist can afford. But keep in mind that this is a lab-grade power supply, and it offers a ton of features you probably won't find on those cheap no-name brand power supplies, and you can bet your bottom dollar it meets all the published specifications. Now let's turn it over and take a look at the backside. On the rear panel, you can see we have this IEC input receptacle with integrated fuse, and here we have a thumb screw for connecting the chassis to the ground. And here you can see all the connectivity this instrument offers. It supports RS-232, RS-485, USB, Ethernet, analog and digital controls. And we'll take a look at some of these features later on in the video. And just for size comparison, I had stacked up the UT8806, which is a 6.5 bench multimeter from UNI-T, on top of the 6953B. And you can see that these two units are essentially the same height. Of course, from the perspective of the camera, the UNI-T 8806 looks a little bit taller, but actually they are the same height. Now, if you compare them lengthwise, you will see that the 6983B, which is at the bottom, is actually even longer than the UNI-T 8806, which is already pretty long. I actually forgot to mention when I was showing you the rear terminals that UNI-T actually provides all the terminal blocks that you will need to connect to the rear terminals. Anyway, with the basics out of the way, let's actually power it on. Now, I think the screen protector is still on. Let me actually remove that first. All right, now let's power it on. You can see that it powered up pretty much right away. By default, it looks like it has these graphical display for both voltage and current over time, which is quite neat. Now, of course, if you want a more traditional display, you can press the home button. You can see that it swaps to this more traditional display. Of course, you can also do the same with the switch button here. I personally prefer this display versus the graphic display just because the fonts here are much larger and I can see the current voltage and current and the power consumption a lot more easily. Actually, let me see if it remembers the display setting after I turn it off and turn it back on. Let's try that. This is actually pretty interesting. You can see the message here on the screen. It's saving some data before shutting down. So powering down actually takes a few seconds. I assume there must be a fairly large input capacitor, as the switch is a physical switch. Now, I think you can turn the display message off though. Let's actually give that a try. Let's power it back on to see first if it remembers the setting. No. It booted into this graphic mode, as when we powered off, we actually were in the other display mode. So let me change it back here. So you can see that, unfortunately, it does not remember the last display state. All right, I just checked the user manual. Indeed, you can turn off that power off message. So let's give that a try. I think you come back here to the menu, and let's come down here, setting. And I think it's this P down. That's the message we're displaying here. So let's come down here, base, power down, and I think we can turn it off. So let's give that a try. And I think that's all you need to do. Let's go back home and let's try power it down again. Yeah, it's kind of disconcerting with the power off message off, especially if you're not expecting this long delay after turning off the physical switch. The power supply was still on. Nothing seemed to happen, at least for a few seconds. Of course, it eventually powered off. Now, I think it probably took the same amount of time to power off, but because there's no information displayed on the screen, so it felt like eternity. Anyway, I actually prefer the default behavior. At least it shows me what it was doing. So let me change that back. Now let's take a look at the front panel controls. The controls are actually very simple and very intuitive to use. For example, to set the voltage, you press the voltage, and here we can set, for example, 15 volts, and you press enter, that's set. And of course, you can also use a rotary encoder to fine-tune the voltage, and depends on which digit you are setting, you can see that no problem at all. And the same thing you can set for current. For example, right now let's just say we're outputting 2 amps maximum, and again, it's set. And then there's over voltage and over current. Of course, they're set the same way. So let's try over voltage. Now, I think the over voltage value has to be higher than the set voltage value. Let's actually give it a try. Let's change it to, let's say, 12 volts. Let's enable that. Let's see what we get. Yep, you can see that the set voltage changed it down immediately because that makes sense, as the over voltage has to be higher than the set voltage value. Anyway, you can enable that, disable that, so on and so forth. Of course, we can change the current protection value as well. And then we'll have this timeout feature, and this is actually useful. It can program the output to automatically shut off once the timer has expired. So let's actually come here and let's enable it. So now you can see that we're currently set at 0.5 seconds. Let's actually change it to, let's say, 2 seconds, just for demo purpose. And the idea here is now if I turn on the output, and it should shut off in 2 seconds. So let's try that. Yep, you can see that now the timer is triggered and the output is powered off. This feature can be quite useful. For example, if you're charging a battery, you want to make sure that the power is off after a certain amount of time, and this is how you're going to do it. Anyway, for today's test, we're not going to use this feature, so let me turn it off. Now the unit is pretty quiet. I don't think the fan is on. Let me see. Nope, right now the fan is not on. Of course, once we start using it, I expect the fan would be turning on at some point. And you probably have already noticed this. There is some residual current reading here, even though the output is currently off. Now, this is actually quite common because of ADC's offset voltage. It all depends on what type of ADCs UNI-T used inside this unit. Unfortunately, I haven't found a way to zero out the current reading yet, and I did read through the user manual, but it doesn't seem like there's an option. It would be nice if you can set it to 0 when there's no load. But the offset value is only a few milliamps, and is definitely within spec. According to the spec, the current readback accuracy is specified as 0.1% plus 25 milliamps. So even with a reading of 4.5 milliamps with no load, it is still within spec. And besides keying in values by hand, like I just showed you, you can also use one of the presets. Of course, you have to set the presets up by yourself. Let's take a look. And here you can see we have 8 slots. You can define different presets, and I had already entered some of these. But let's say we want to change one of these. So let's go down to the 24 volts. Let's say we want to change it to over voltage protection of 24.5 volts instead of 25 volts. So let's do edit. And you can see here, we can set the OVP. And let's say 24.5, enter. Whoops, 24.5, enter. And now this value changed to 24.5. So you can see that it's pretty easy. And now let's say if we want to load this, actually let's escape. And we just simply press load. And now you can see that the voltage is set according to the preset values. Of course, we can also change it back. I don't know why every single time it changes to this graphic display, and it doesn't quite remember what you selected last. But anyway, we can change it back and forth by pressing the home button. Let's put on a load and verify the readings. Now, I could use an electronic load, but for this test and the next few tests, I think I'm going to simplify things a little bit, and I'm going to use a 100 ohm power resistor, as it is purely resistive and also it doesn't generate any additional noise. So we can see that whether or not the fan spins up or down depends on the load. Anyway, I will use the electronic load later on when testing the maximum output power. Actually, before I forget, let's verify whether or not the binding post spacing is standard. Let me find my adapter here. Yeah, as you can see, no problem. Now, some Chinese power supplies, especially the cheap ones, I noticed that the binding post spacing is actually not standard. I don't know why, but it's good to see here we're following the standard. Now let me plug in a couple of cables. And oh, by the way, the binding posts actually look very nice. You can see these ones don't come off, and they do have the holes on the top. You can't see this, but you can insert wires into the binding post and you can twist it tight. Anyway, so let me put in a couple of cables. And here I have a 100 ohm power resistor. Let's clip it on. And let's enable the output. Yeah, you can see that. We get some readings. You know what I'm going to do? I'm going to bring down the UNI-T UT8806 6.5 digit multimeter, and we will actually put it on site and verify some of the readings. Give me a second. All right, I have hooked up the bench meter. Actually, before I connect anything, let's actually verify the output voltage set accuracy. So let's change the voltage setting here. And right now you can see we're at 24 volts. It's no problem. Let's actually go back to 1 volt. And the output changes really fast. Actually, that's good because for some power supplies, it takes a while for the output to ramp down. And this one is pretty fast. Let's actually go all the way down to 0 volt. At 0 volt, you can see that we only have about a 0.12 millivolt DC offset. So that's actually excellent. Let's do 0.1 volt. Yep, pretty accurate. Let's do 0.5. You can see that it is pretty much spot on. And let's do 1 volt again. And let's do 5 volts. No problem. And 10. Excellent. Let's do 50. That's really good. And let's do 100. And now let's bring it to the maximum, which is 150 volts. And you can see that over the entire range, the voltage setting is actually very accurate. Now I have essentially shorted out the output. You can see that we're in current measurement mode. And right now, with the current setting output to be 0, we do get some offset, and we're roughly getting around 6 odd milliamps. Remember, as we mentioned earlier, the current accuracy is actually 0.1% plus 25 milliamps, so this remains within the spec. But nevertheless, it's not ideal because we currently set it to output 0. So let's actually take a look. Let's do 1 milliamp. Can we register that? Nope, we can't. 2. Nope. 3. 4. Nope. 5. 6. 7. 8. 9. 10. Yep, you can see at 10 milliamp we did register that, but before that we were not able to register anything. So there is a minimum threshold, but of course, as I mentioned earlier, this is still within spec. All right, so let's do 20. And you can see as we start increasing the current output, the reading is going to be more and more accurate. 30, 40, 50, 60, 70, 80, 90. Let's do 100. At 100 milliamps, we're 4 milliamps out. So let's do 500. And we're still 4 milliamps out. So it seems like that is a constant offset. Let's do 1 amp. Yep, we're still roughly 4 milliamps out. Let's do 5. Actually, 5 is quite accurate. Let's see, 2. So gradually, you can see it's becoming more and more accurate as we increase the output current. At 2 amps, we're only about 2.5 milliamps out. 3, we're only about 1.7 milliamps out. 4, now we're actually pretty much exact. 5, 6, 7, 8, 9, and 10, that's the highest. Actually, Right now, I think we got to 10.5. Let's go down 10, because there is a little bit of margin built in. So you can see that the output current and voltage display are actually extremely accurate. All right, now I have connected the power resistor. You can see currently we're drawing 0.1 amp. And the UNI-T bench meter is actually displaying the voltage measured at the terminal here. Of course, there will be some discrepancy as we're only using 2-wire measurement. So as I increase the voltage, as the current draw becomes higher, the voltage measured on the UNI-T 8806 will be lower than what is displayed here. Of course, we can always break out the sensing wires on the back of the unit and connect it directly to the load, and that will actually help the measured voltage. But anyway, we're not doing that in this video. So let me increase the output voltage. So let's go to volt. And I'm going to do 10 volt at a time, 20, 30, you can see it. It's still pretty accurate, 40, 50, 60, 70, no problem, 80, 90, 100. So that's actually pretty good. You can see the readings remain pretty close to what the nominal value is. Of course, this is a 100 watt resistor, so I probably shouldn't be increasing the voltage much beyond this, but let's give it a try here. 10, 20, 30, 40, 50. Anyway, pretty good. And by the way, this power supply actually has active power factor correction built in, so the power factor should be quite decent. Let's actually take a look at the power factor here. So for that, I had plugged it into a kilowatt, you can see here. And currently, I'm not drawing anything yet. It's showing that power factor is roughly 78%. So let me enable the output here. So we're still at 70 volts, and this will draw quite a bit of current here. Let's turn it on. And you can see that we are actually approaching 98%. That is excellent. So to the power grid, the 6953B almost is purely resistive. Anyway, if you have a thumb drive, you can actually store the current screenshot on the drive itself. And that's actually quite useful for documentation purpose, especially when you are doing some documentations on experiments or doing product verification. So let me actually show you that briefly. So for example, right now I plug in a thumb drive, and then you can long press the menu button to take a screenshot. So this feature is actually quite neat. What is funny is I think the fan in the 8806 is actually a lot louder than the fan in the 6953B. Since we have already verified the output current and voltage accuracy, I'm going to power off the 8806 and concentrate on the 6953B. The UDP6000 series has overvoltage protection, as I mentioned earlier. Now, obviously, during normal use, it will not kick in. Overvoltage protection and overcurrent protection, for that matter, typically are handled by separate circuitry inside the power supply, so that in the event of malfunction that caused the output to exceed the overvoltage or overcurrent settings, the control circuitry can shut off the output and thus protect the connected equipment. Now, here I have a trick that we can use to test whether or not the overvoltage protection is working correctly. Because this is a single quadrant power supply, meaning that it can only source current but not absorb current. So you can connect a voltage that is higher than the output. If the power supply is properly designed, this shouldn't be an issue. The power supply simply won't do anything, as the output voltage is actually lower than the connected voltage. But the connected voltage should be reflected on the measured voltage on the display. And when it's higher than the overvoltage setting, it should cut off the output. So let's actually give that a try. And what I'm going to do is I'm going to use a 9-volt battery to simulate the higher voltage here. So to do that, I actually need to set a voltage here. Let's set it to, let's say we want to output, 9 volts. Actually, let's do 8 volts. And we want the over voltage protection to kick in at 8.5 volts. Yep. And now let's enable the over voltage protection. And let's connect the battery here. And you can see that the output is shut off. And that makes sense because the battery voltage is higher than the voltage protection limit. And next, I want to test out the power on characteristics. For that, I need a scope, so let me hook that up and we'll be right back. And by the way, I just hooked up the oscilloscope to the power supply output via this BNC cable. And before we do the power on characteristics measurement, let's actually take a look at the ripple noise. And for that, I actually changed the scope to AC coupling, and you can see here, I'm setting it to AC coupling and bandwidth limit 20 megahertz. As if I don't enable the bandwidth limit, I think the noise is going to be a lot higher. Let's see that. Yeah, you can see the noise is way higher. So let's enable the bandwidth limit here. And by the way, the noise you see here is actually not all coming from the power supply. Some of the noise is actually coupled in from elsewhere. And of course, because right now there's no load connected, and the noise is actually higher than what it's supposed to be. So just to prove that, I'm going to connect the output to this resistor here. And you can see that the ripple noise is actually lower now. Now let's actually do some measurement here. So I enable the voltage measurement and turn it on. Okay. And we're not showing anything yet. Let's actually configure the cursor here. I don't think I selected it. No, I didn't. Okay. So you can see currently we are measuring about 44 millivolts. Now, obviously the ripple noise we're seeing here is much higher than your typical linear power supply. But for a switching power supply for this 6953B, it's actually pretty decent. If you look at the spec, the maximum ripple noise is actually specified as 50 millivolts peak to peak, and this is within that. Now you may say that 50 millivolts peak to peak is actually pretty high. I suppose that's all relative, because this specific power supply is rated for 600 watts, and naturally it will be a little bit noisier compared to a lower power one. So if you don't need all the power, you can actually go with the, for example, 6952B, which happens to be the cheapest model. The ripple noise of that model is only 5 millivolts peak to peak. But of course, the UDP6952B is only rated for 100 watts. So just keep that in mind when selecting your switching power supply. Anyway, now let's take a look at the power on curve with this 100 ohm resistor at 24 volts. Alright, now I change it to DC coupling, and also the horizontal, change it to 10 millivolts per division. So let's do a single shot. And you can see that the ramp up looks perfect. The slight jump here, that's because I set my trigger level to right above here. So let's do some measurement here. Let's do time, switch on, and let's see here. So you can see that rise time is roughly 26 milliseconds. And let's do that again. So let me turn it off and turn it back on again. You can see that the power on curve is very clean. One unique feature of this power supply is that you can actually change the slew rate of both the power on curve and the power off curve, and you can do that for either voltage or current. So this is actually very useful, especially when doing certain tests. Some circuitry, for example, don't handle power rail with slow ramp-up time that well, and it's important to be able to quantify the timing. And that's just an example of how this feature can be used. Anyway, let me actually demonstrate this feature here. So let me turn off the output. Let's go to menu, and let's go down to output. And here you can see we have this SR mode normal. So what we want to do is we can change the SR mode. Let's say we change it to constant voltage slew rate. Of course, we can also change it to constant current, but for this demonstration, let's stick with constant voltage. So for that, the rise time right now is actually only 0.01 volt per second. Let's actually change it. Let's do SR edit, and rising, let's change it up. Let's do actually 100 volt per second. And for the falling, let's do the same thing here. So let's do 100 volt. So with this setting, if we turn on the power supply right now and do another single capture, we should see that this ramp becomes less steep. So let's give that a try. Yeah, you can see now we're actually taking a lot longer for the voltage to ramp up. So let's actually, what we'll do is let me do this, and we'll do another capture here. And you can see right now the ramp up time. is roughly 216 milliseconds. And given we're outputting 24 volts, give or take, this number is actually in the ballpark. Advanced features like this you probably won't find on any of the entry-level power supplies. Let's actually change it back to the default. I was just reviewing the recording and realized that I actually forgot to test one more scenario. And here I set the voltage output to 50 volts, as you can see, and also the current limit is set to 100 milliamps. So what I wanted to test is if I connect the 100 ohm resistor to the output, obviously the voltage would drop to around 10 volts, given the current limit. What I want to see is what the waveform looks like when I turn on the output. So let's give that a try. So right now I have connected everything up. The scope is in single shot mode. So let's turn on the output. And you can see we did get an overshot here. And the highest voltage is actually around 27 volts. So for a brief moment, we are actually outputting around 2.7 times the current than what is limited at. So let's actually take a look at how long it took for the current to drop back down. So let me enable the cursor here. So let's do time. Yep, turn it on. And let's see, we power down here, roughly. And let's just say here is good enough. So it actually took around 250 milliseconds for the voltage to drop back down. So in this case, while the overcurrent is brief, it could still damage some sensitive equipment because after all, it took over 200 milliseconds for the current to ramp back down. So now let's actually take a look whether or not overcurrent limit would help in this situation. So for this test, I enabled the overcurrent protection here. You can see that is set at 110 milliamps. So let's power it on and see if we get a different curve. Nope, it seems that this did not kick in. So let's try it again. Nope. How about we set it at, let's say, 100 milliamps, and let's give it another try. Yeah, you can see actually the overcurrent kicked in, but the problem here is actually it took much longer for the overcurrent to shut output. So how long it took? Let's see here. It took roughly 573 milliseconds. So this test just tells you that even with overcurrent over voltage protection, you still need to be very careful when connecting to your test equipment, because sometimes all it needs is a few milliseconds of over voltage, and that could potentially damage your sensitive board. All right, with the basic features out of the way, let's add more load and see how well the power supply handles that. Of course, because the power supply is rated for 600 watts and I don't have a single electronic load that can handle that much power by itself, so I'm going to use a couple of these to generate the load required to test this power supply here. And also, we haven't really seen this graphic display in action just yet, so I think this might be a good opportunity for me to showcase this graphic display with current, voltage, and also power consumption over time. And also for simplicity, I'm setting the output voltage to 60 volts, you can see here, so that we can actually absorb the maximum current of 10 amps at the maximum power consumption of 600 watts. All right, so with the settings out of the way, let me enable the power supply here. And you can see that we're currently outputting 60 volts. And first, I think I'm going to start this electronic load here, and it's set as 5 amps. So let's enable it. Now you can immediately see we are drawing 5 amps. And of course, the display here, you can see we are displaying both current and voltage. That is actually a little bit confusing because you can see here, let me zoom in. You can clearly see on the side here, we are displaying both current and voltage here. So it depends on which curve you're looking at, you need to take a look at the unit here accordingly. And the power consumption is displayed at the bottom here. Okay, so now let me enable the second electronic load here. And I'm going to ramp up the current. And you can see we're gradually drawing more power here. So now we're actually drawing more than 600 watts. And you can see the current is just above 10 amps. And I don't know if you can hear or not. Oh, unfortunately, the fan of this electronic load kicked in, but I did hear the fan of the power supply actually started to ramp up a little bit. But nevertheless, it's actually still very quiet compared to the electronic loads fan. So I'm going to let it run like this for a while. In fact, I can probably still increase the current on this electronic load a little bit because this one is rated as 400 watts. Currently, we're only drawing about 300 watts. So let me do that. So let's actually set the current here. And let's see if we can do that here. Increase a little bit more. Yep, right now actually we triggered the constant current mode. So let's dial it down a little bit. So this is actually 5.1 amp. This is roughly the maximum we can draw from this power supply before it enters constant current mode. And as you can see here, everything is holding up pretty well. Remember, the maximum specified power for this power supply is 600 watts, and right now we're just above that. I'll let it run for a few minutes, and let's see if we have any problems. I took a break and I came back. It's probably been running like this for at least 15 minutes now. You can see that no problem whatsoever. Of course, the one thing you notice is that at this high current, obviously there's some voltage drop across the wires. You see that on this electronic load. This one is actually the first set of the plugs, so that's closer to the power supply's output, and we're registering 59.42. And the second electronic load you can see here, we're only showing 58.9 volts, and that's all because we're not sensing the voltage at the terminals here. So if you want to ensure the voltage at the load is what is displayed, then what you can do is connecting the sensing wire from the terminal block at the back of the power supply to the load itself, so that you can actually compensate for the voltage drop across the wires and get an accurate reading at the load side. And now I have set the voltage up to 148 volts. Of course, this unit is capable of outputting 150 volts. And the reason I set it to 148 is because the maximum voltage accepted by this electronic load is only at 150 volts. So I wanted some margin here. So anyway, let's enable the electronic load here, and let's see how we handle at this high voltage. Of course, you notice now the maximum current can be set is currently limited to 4.1554 amps. And that's actually automatically adjusted because the maximum power envelope is 600 watts. All right, now let me enable the electronic load. And we're going to enable this one as well. So now you can see we're drawing just shy of 600 watts. Of course, we can push the current on this load a little bit because this one is actually rated for 400 watts. So let's do that. Let's come here, 2.1 amp. And right now we're above 600 watts. And you can see that everything is holding up pretty well. Again, we'll let it run for a few minutes. And again, it has been running for a few minutes now. I do want you to hear the fan noise of this UDP6953B. So I think for that, I'm going to actually just power off these two electronic loads so that you can hear, at least right now, what the fan sounds like. So let me do that right now. And you can hear the fan noise is actually not that bad on this UDP6953B. It's actually relatively quiet. So this is pretty much what you can expect at full load. And just like a lot of the professional power supplies, this power supply also supports the list and delayer functionality. And here we're just going to take a quick look. There's just so much detail in this specific functionality. If you're really interested, I'd recommend you check out the user manual. But the idea here is you can generate a list of voltage and current settings, and you can output that accordingly according to the timing you set at the dwelling interval here. And of course, you can manually edit this list by hand. Of course, that's not going to be very convenient. It's going to be very tedious. Luckily, you have the ability to edit a spreadsheet and upload it through the web interface. So let's actually take a look at a few pre-built ones. If you come here, you go to template, you can see that we have a bunch of pre-built waveforms, and this first one is sinusoidal, and you can do pulse, so on and so forth. And of course, for each one of these, you can also change it to output current or output voltage. So once you select one of the waveforms, for example, right now we have the sinusoidal, and the parameters here, the minimal is 0 volts, and the maximum is 152 volts. So what it will do here is it will generate the sinusoidal waveform between 0 volts and 150 volts in 512 steps at an interval of 0.1 second per step. So let's generate that. And once the waveform is generated, you can come back to the list, and you can see that now we have the voltage steps in a sinusoidal fashion. So now you can run this. So one issue I found is that for whatever reason, the generated list, at least initially, the current is 0. So you wouldn't see an output waveform. And of course, you have to change the current to a non-zero value so that the output becomes constant voltage instead of stuck in this CC mode. And this is something really easy to fix if you are uploading this through a spreadsheet. But unfortunately, through the UI, it's actually going to be a little bit difficult to fix because you have to go in here manually and change each of the current values like this. So I'm not entirely sure why this is the case, but right now if I run it again, you can see that. Let's go back. And whenever we hit that 1 amp, you will see the CC get turned off. We have to be a little bit patient because I think that's 100 something here. Yep, you saw that, and that's because we set the current to 1 amp, and that's actually how it's supposed to work. But nevertheless, by default, the generated voltage list does not have the current setting. And of course, if you click on the list again, it will come to this menu and it will show you the state of each one. You can adjust whether or not the default state is off or on. So that's the delayer and list functionality. So this feature is actually going to be very useful for automated testing, as you can preload a predefined time series of voltage and current values and then test your circuitry. As I mentioned earlier, this power supply can also be controlled externally via the inputs from the rear panel. And this feature is actually quite useful as well for test automation. And the UNI-T UT6000 series can be controlled via either analog or digital signals. So let me give you a quick demonstration and show you how to use potentiometers to adjust the output voltage and current, just like you would with your old-fashioned bench power supplies. And in the user menu, you can see here, it shows you how to do that. Here, I have built the circuitry. As you can see, these are the two potentiometers, and here is a on-off switch. And of course, I have wired it up according to what is shown in the user manual. And this is a terminal block I'm going to plug into the rear. So let's give that a go. All right, I just connected the control board to the power supply, and you can see in this picture here. So now we should be ready to control the power supply using this breakout board. Of course, to do that, I have to change a couple of settings. So let's actually go back to the menu and see how we do that. So you can see here we have an output option. Let's go down, and we press on mode. You can see we have essentially 3 options: normal, which is controlling everything via the front panel, and then we have XV and XD. XV is to control the power supply via external analog controls, whereas XD is controlling everything via digital controls, which we're not going to cover in today's video. Anyway, let's take a look at XV. So once I enable that, let's go back here. So now in theory, we should be able to control the power supply using this board here. And let's actually turn on the power supply here. And you can see that the power supply turned on. To adjust the voltage here, I'm just going to use the first potentiometer. And by the way, I hooked it up backwards, so you can see right now I'm doing counterclockwise and the voltage is increasing, but that's actually not a problem here. So you can see that we are able to adjust the voltage here. And similarly, this potentiometer also controls the current here. So you can see right now the setting is at 5.39 amps. So let's adjust that. You can see, not sure how clear you can see. Let me zoom in. You can see that we're essentially changing the maximum current here. Anyway, so now you can see we can change the power supply settings via these external analog controls, which is kind of cool. Of course, while you are in this interface, if you press the front panel buttons, for example, if I change it to off, immediately the external control will be disabled. Now, for example, I can no longer control the unit using external control unless I go back to the menu and reset the output option to, let's say, EXTV. After that, you can again control the power supply via this board. So basically, if you press any key on the front panel, you cancel out the external control. This power supply can also be remotely controlled over Ethernet, and for that I just hooked up a Ethernet cable at the back here. Unfortunately, it does not support wireless control, so that you'll have to use a cable. Anyway, let's go to the menu and let's take a look. So in menu, let's come here to the settings, and you can see it already automatically acquired the IP address, so we should be able to connect to the computer here. So let me show you that. Now, hopefully you can see on the computer here, that's essentially the user interface of the power supply here. Control here is quite rudimentary, but you can definitely set any one of these. For example, right now, the voltage is set at 143 volts. Let's set it to 50 volts. And let's see if we get reflected here. And not yet. So I think I need to submit. Yep, you can see now the voltage here changes to 50 volts. Of course, we can change the current and also voltage current limits. Let's actually turn on the output. Yep, you can see the output is on. Of course, we can turn it off. And here we can go to the list and delayer. So here, obviously, it can be set much more easily as you can come here and edit the different settings instead of having to key them in one by one. Of course, we can make this screen smaller and you can see everything here. So the web interface here essentially replicates all the functionality found on this power supply. And you can also go to the settings here. So you can see that we can change a lot of the settings via the web interface as well. Alternatively, you can also control the power supply via the instrument application supplied by UNI-T. Of course, this one does involve an installer here. So once installed, you launch the application and here is what you see. And we can scan it. Let's see if we find this power supply here. Again, it asks for IP. Let's hit go. Yeah, you can see that it identified we are connected to a UDP6953B. So let's launch it. This user interface, I think, is a little bit more polished than the web version. It's a little bit more interactive. As you can see here, we're updating the list as we speak. It is in real time. And here, of course, we can change the voltage. Let's change it to, let's say, 60 volts. Did we change? Refresh config. Yep, you can see now it changed to 60 volts. And let's change the current, let's say down to, you can also drag this, 2.627 amps. And we refresh, let's take a look. Oh, it's already changed. Hang on, is it automatic? No, it's not. Let's see here. That's interesting. Okay, so it does update once a few seconds. So now you can see here, even without refreshing, now we change to 1.52, which is what I set here. So now let's actually drag the voltage down a little bit. So let's do, let's say 52 volts. Yep, it also changed. So by the look of it, actually, you don't necessarily need to refresh. Everything is updated in real time. So that's good. And now let's see if we can enable the output. Yep, you can see that the output turned on. Also, we can turn it off right here. One thing cool about the instrument application is actually you can see here, you can change the slew rate of the output from the drop-down menu right here, instead of having to go into the configuration to change it. So that's excellent. Using the instrument application, you can also set up the delayer and also list function very easily. Let me show you that. For example, if you click on the programmer here, and you can actually edit your list, and also you can come here and change your delayer settings. And all these can be done very conveniently through the user interface, instead of having to do it through the buttons on this power supply itself. Of course, the UNI-T6900 series also supports the standard skippy commands as well. I'm sure there's still some features I haven't touched upon yet, but from what you have seen so far, I'm sure you can all agree this is a very capable power supply. This video is already getting pretty long. I think I'm going to wrap it up by opening it up and take a look inside. The case was just held in by a few of these hex screws at the back, but in order to disassemble it further, I ended up taking out more screws. Now, I decided to stop because this instrument is so beautifully put together, and I don't think I can put everything back the way it was originally assembled. And also right now, you can pretty much see everything already, so let me walk you through some of the key components. Right now, you are looking at the main board. and you can clearly see the build quality is impeccable, and everything is very well put together. I bet if Dave is watching this video, he would say it is a Bobby Dazzler. Anyway, if you follow the wires, you can see that the mains voltage comes in through these wires from the rear panel, and then is being switched by this physical switch. The high voltage section of the board and the low voltage section of the board is separated by this white line here. You can see the L-shaped line. On this side, that's the high voltage section, including all these switching elements, and the low voltage section is in this corner up here. The thermal design is actually very clever in this power supply, as you can probably see this plastic shroud over the heat sinks, and that's for guiding the airflow. We also have a couple of fans for guiding the airflow. One is here, vertically mounted, another one is mounted on the rear panel, right here. So during operation, the rear fan sucks in the cold air and blows through these two heat sinks, and then the air gets further relayed by this fan here, and it blows through within the entire shroud. So the airflow in this unit is actually very efficient. And here you can see a couple of these massive chokes. And here you can see the main controller board that's on a separate PCB right here, and it's mounted in parallel to the main PCB. This adds additional rigidity compared to, say, mounting it vertically. Of course, UNI-T has the luxury of doing that because there is plenty of space inside this power supply. The main switching component on this board is right here. It is a UC3825, which is a high-speed PWM controller. I did take a quick look at all the chips on this board here, but I couldn't quite read all the markings on the chips here, unfortunately, and I didn't see a dedicated ADC chip. So perhaps the ADCs used in this unit are actually located on the front panel circuit board. And back here we have a 7812, which is a 12 volts linear regulator. You probably also noticed that we do have a couple of filter caps missing. One is here, and the other one I think is right here. You can see we didn't have this one, nor this one. I'm not sure if these caps are reserved for the other models, or they simply decided these are not needed for the specs given. From the silk screen on the board though, you can see this board is actually specifically made for the 6953B. Let me show you here. And here is the silk screen. You can see UDP6953. I originally was trying to remove the front panel board to get a better look, but the connector here unfortunately has select stick on and I couldn't quite remove it. Also, everything else which is put together so beautifully, so I decided not to take it apart any further. Anyway, you can pretty much already see everything on the board. I'll put a close-up picture on the screen here so you can see it better. The microcontroller used on this board is this 32750, which is an STM32H750, an ARM Cortex-M7 microcontroller. It does have built-in 16-bit ADCs, so I'm not sure if UNI-T is using the built-in ADCs for current and voltage readback. And here you're looking at the board for the rear panel. The chip here is an ADUM4160, and that makes sense as we have a USB connector. And the chip here is a MAX232, which is a RS232 driver. That also makes sense because we have a RS232 port as well, and the other chips are field isolators. That's pretty much all I want to cover in this video. Of course, I'll have to put it together off the camera. Please leave me a comment in the comment section below if there's anything else you would like me to show you of this power supply. I think the UNI-T UDP6953B is a fantastic switching power supply. It's powerful, accurate, lightweight, and has a ton of impressive features. Well, that's all for today. I hope you enjoyed the video. If you liked it, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.